Okay, so good morning. My name is Sijia Geng. I'm an assistant professor from Johns Hopkins University in the United States. I obtained my PhD from University of Michigan, followed by 1 year stay in MIT, and then I moved to Hopkins in 2023. So today I will share a topic on power system stability with high shares of grid-forming and grid-following inverters. This follows within my research expertise. My main research focus is on power system dynamics and control. So this lecture will be divided by two parts. The first part will be on fundamentals. The second part is on advanced topics. So I attended the poster session yesterday, and I realized you are coming from vast, very diverse research areas. It's not reasonable and probably too ambitious to try to make sure everybody fully understand dynamics and control, which is by itself a very difficult topic. So my aim is to lay a foundation and hopefully to inspire you to appreciate this is an interesting topic, it's a different topic, and it's a difficult topic, and it's an important one to industry and academia. So feel free to interrupt me in this lecture. The first lecture will be around, we have 75 minutes. I will try to keep it within 60 minutes or 65 and leave also some time in the end. With that, here is the outline of the lectures. The first one, I will spend some time to introduce the background on power systems with high shares of inverter-based resources. And then I will explain the modeling and dynamic responses for grid-forming and grid-following inverters. And then I will spend most of the time on introducing the fundamentals of stability concepts. Okay, let's get started. Can you hear me well from the back? Okay, great. So the foundations of power system are changing with the gradual retirement of fossil fuel-based synchronous machine and the fast adoption of inverter-based resources, including renewables, electric vehicles, a long integration sequence of data centers, and electric vehicles, all you can name it. The synchronous machines are the traditional generator to support and generate power in power systems. And it has this large rotating machine. And we have the natural voltage source forming behavior. We have a large fault current that are inherent to synchronous machines. We also have inertia that's associated with this large rotating mass. All these are good physics. And they will all be lost with the retirement of synchronous machines, unless we put them back through clever design of control on these power electronics devices. Let's look at these two figures, which is type 3 and type 4 wind turbines. Although we still have this physics, this rotating part, but as seen from the system operator's perspective, the dynamics of this rotating part is more or less decoupled from the system dynamics. And what's more important now is the control we enforce and designed for these power electronics interfaces. This is true for both these two types of wind turbines. This is also true for other type of inverter-based resources like battery or electric vehicle, data centers, etc. So we have a very large room of flexibility for this control design of these power electronics, because now we are not restrained by the physics, the Newton's law for this machine. Now we have a large room of flexibility. This is both blessing and a curse. What do I mean by that? Although we can achieve a lot of things, we are not restrained by the slow response of this rotor. But now we have to make sure that all these different type of controls, they are interacting with each other well across the network, and the entire network is stable. Later, we will explain why stability is important for the system. So at one end of this spectrum, we have grid following control, which is the most popular and the dominant technology for majority of the IBRs connected to the grid at the moment. It is a current source, meaning it injects active and reactive power to the grid. For example, consider your rooftop solar. Whatever power that can be generated at this current moment, we want it to be fed into your grid. So it has the name of follow because we assume there is an existing voltage and a steady voltage waveform available. And we want to follow this voltage waveform, meaning we will estimate this voltage, including its phase, its voltage, and then we try to construct this current to inject the desired active and reactive power. So immediately you would realize if this voltage waveform is not steady, meaning if it's susceptible to disturbance when I inject another current, this would cause problems. So a typical issue is poorly damped oscillation in weak grid. This is the drawback of grid following. On the other end of the spectrum, we have grid forming control, which is viewed as the future of this inverter-based technology. It tries to actively form the voltage source behavior, meaning its magnitude and its frequency. So it is a voltage source by nature. It has the advantage to support a weak grid, and it can also achieve black start capability. Note that, though, this is not a binary distinction. There are numerous ways of achieving control for inverter-based resources. One specific example is this unified grid forming, grid following inverter that we proposed some years back that unifies the feature of grid forming and grid following inverters. It tries to inject the active power and voltage magnitude. In a sense, it's similar to what a synchronous machine does. These are also specific examples. You have many other flexibility in designing control, as long as you make sure the entire system is stable. Okay, so we are yet to understand these new forms of dynamics and potential instability that are introduced by inverter-based resources as compared to in the traditional way, the swing dynamics of synchronous machines. This is challenging because of this flexibility in control from these all popular control schemes, among others. And we also lost the classic timescale separation in traditional power systems because now the IBR operates in milliseconds timescale, which may interact with the line dynamics and the filter dynamics. Also, they have power electronics-based operational limits and characteristics. These I will also come back later. So the traditional tools for analyzing and ensuring stability in power systems may soon become obsolete because in the past, we rely on a set of pre-screened operating points, and we focus our computing resource to study these scenarios for large-scale power systems. Now, in the future, systems that are dominated by renewables and this load flexibility, you may face a high level of variability of your system condition. And also the system complexity and nonlinearity also increase with this heterogeneous of IBRs. And last but not least, a very important challenge is that system operators are facing a much higher model uncertainty. Because these controllers that OEM developed, they spend a lot of engineering hour in designing their control schemes. They do not want to share this to the public. So as for the perspective of system operator, you need to make sure the stability of a large-scale system with a more or less gray box model. Okay, so that's the challenge. That's why system operators from around the globe are experiencing more and more issues that are attributed to inverter-based resources. For example, as seen by this figure, this is a recording by AEMO, the system operator in Australia, for various occasions of subsynchronous oscillation in West Murray Zone, which is an area in Australia that has high shares of renewables, and that is a little bit further from the main grid. So as you can see from this figure, it shows for some time period the wobbling of the signal. So in technical term, we call it sustained oscillation. Meaning in an ideal situation, you would want, when the system is subject to a disturbance, this signal to be quickly damped out and converge to your desired point. But instead, in this figure, it continues to wobble and sustain. This is not an ideal situation because that means this is a weakened condition. If there's additional disturbance or fault to your system is more susceptible to issues. So we want oscillations to be damped out quickly. Okay, and another interesting point to mention here is people typically study subsynchronous oscillation using linear tools. However, when you see sudden occurrence and disappearance of this oscillation, there's got to be nonlinearity inherent to it. And let's see the situation in the load side. The power electronics load behaves like constant power. And I want to highlight that this is constant power not by physics, but it's by control design. So the control loops make them appear as constant power. There's no physical constant power load. So imagine your electric vehicle charger or the energy efficient lighting, they more or less consume the constant power from the grid based on their control mechanism. Why this could be a problem? Let's look at this example. This is a classic single inverter infinite bus system with an additional load bus in between. If this load were a constant impedance load, then it can be absorbed into the line parameter, and the dynamic would be similar, the characteristic would be similar as if this were a single machine infinite bus system, right? So look at this characteristic curve. This is power of the machine versus the angle, and that's the blue curve. This is still sinusoidal. If you recall, if you have taken a power system dynamic course, this is similar shape as the characteristic curve for single machine infinite bus with just a phase shift, which you can see here. But their structure are the same. However, if this load were a constant power load, then the structure of the system changed. Look at this green curve. Maybe at this part is more or less similar, but the shape over here is completely different. It fold over, and also there's a smaller range of this allowable operating range. What does that mean in physics? If your angle somehow got to dragged into a larger angle than this bifurcation point, you wouldn't have a solution in your mathematical model. And in physics, that means your system would collapse. Okay, so this is called a structural instability. And I will also try to reserve some time to talk about that. Okay, so in addition to this type of structural instability, there's also other more intricate considerations. For example, the protection mechanism of your EV charger. If the grid voltage experiences a drop or disturbance, the protection mechanism of your electrical load may decide to disconnect from the grid to protect itself. But as seen from the grid, this is an additional disturbance in an already challenging situation. and that's additional challenge for the system stability. Okay, so that's a quick introduction, hopefully to motivate you about the challenge and the state of art for these future power systems that are dominated by power electronic devices. Next, I will devote this section on the modeling and dynamics of grid forming and grid following inverters. So the IBR architectures, although there could be numerous control schemes, they can generally be presented using this generic scheme as shown here. It features a voltage source converter connected through filter to this PCC point, which is point of common coupling. And at this PCC point, we want to achieve or enforce certain desired behavior. For example, constant voltage or certain active and reactive power injection. And then here is the external grid. Connect through a transmission line to the external grid. Okay. And we have a variety of possibility for this grid interaction functions, and then the the internal IBR controllers, cascading voltage and current controllers. I don't mean that all the blocks has to be active for all the controls. This is just a generic scheme you can use to help with your understanding. So the timescales for a typical IBR is listed here. The inner current is typically the fastest loop of the timescale of 1 millisecond to 5 millisecond, which is here, the inner loop, typically current controller. And the outer loop voltage controller is, in general, 10 or 20 times faster than the inner loop controller. This is also control rule of thumb. Your outer loop controller should be slower than the inner control loop. Okay, and the dynamics of power is typically 100 millisecond or 500 millisecond, roughly. And generally, the bottleneck is PLL. So the PLL loop cannot be too fast if you think about the logic of how it works. If it's too fast, you may have instability issues. There has been a significant effort at the moment in developing different grid codes for inverter-based resources. This is still an ongoing effort, and it's been evolving at the moment. So, for example, NERC, North American Electric Council, they defined the GFM functionality as the follows. The GFM IBR controls maintain an internal voltage phasor that is AC voltage magnitude and angle that is constant or nearly constant in the subtransient to transient time frame, which is basically a subsecond. So this is more descriptive expectation for GFM, right? But it wants, you can see, a constant voltage phasor, both magnitude and angle at the PCC point. And the Unified Consortia, which is a consortia in the United States that are focusing on the testing and standardizing GFM technology, they define these various functionality expectation for GFM and GFL inverters. This is a draft at the moment. So as I said, this is an evolving field, both in industry and in academia. Okay, but similarly, you can see that it asks the GFM to maintain desired voltage phasor within 5 cycles, which is roughly 100 milliseconds. The importance of this GFM support happens in this shorter period. If you move longer in time, other type of devices may be able to come to help. But most importantly, this is the most critical response that we need to replace the physical and the natural inertia response from the synchronous machine. Okay. And here is a Greek code for battery energy storage system. BESS is very promising, is the most promising technology to achieve GFM in the real world. And NERC defines 3 core functional performance tests for GFM battery storage systems in terms of their observable responses of these important electrical states: frequency, voltage, phase, or angle. And the details are described here, which I will skip. You will have access to the slides and probably also recording later. And here is a summary of the Greek code from around the globe across different regions and organizations. This is somewhat more quantitative as for their expectations or requirements on quantities such as Rockoff, angle, phase, step. When this is being used to test your device, what should you expect as a response from your IBRs? And system strengths and other considerations. And if you want to look at more details, zoom in even a little bit more, here is the example model, 9th order model for a PLL-based grid-following inverter. The equations are listed here. It's probably too hard for you to see. And here is the general structure, the control scheme for this particular execution of PLL-based grid-following inverters. The PLL is the block that is used to estimate the angle of the grid voltage for your device to lock on. There are many different ways of achieving PLL, including linear PLL, nonlinear PLL, or digital versus analog. There's a popular PLL that's using signal multiplier. When you multiply two trigonometric signal, you get two frequency. One is double the base frequency. One is the difference. So if you filter out the high frequency signal, you get this difference. And that's what you can use to achieve this lock-on. Okay. Here is an example of Joule-based grid forming control with these modules, for example, on DC link modeling over here. And various detailed consideration of limiter and anti-wind up. I will also come back to this later. Here is an example of virtual synchronous machine-based grid forming model, which is another popular GFM control scheme. Again, here is the possibility of including the DC link model and the other, for example, the grid interacting function includes a virtual synchronous machine and the voltage loop. And the inner control loops has DC link control and the voltage and current controllers. I want to spend a little bit time on this topic because it's very important and it's a distinctive factor compared to synchronous machine. For synchronous machine, you can sustain a fault current of the level as high as say 5 to 7 per unit of your nominal current. But for power electronics devices, if you're exceeding somewhat small amount of current through your power electronics, you may risk burn out this device. And this is a critical point. And typically the level for IBR is very low to the level of around, say, 1.2 per unit. So here are various engineering ways in the literature and in practice to achieve this current limitation. In the second lecture, I will present a research project that use control theory to rigorously ensure the satisfaction of current limit. But let's firstly see what are the existing approach. Look at here. Here is a reference justification. You modify the reference for the current that you would want to cap it such that hopefully the actual current signal will be within the bound. There are three different ways as shown here. Instantaneous, which is map back this current vector down to this rectangular box. And there's magnitude-based, which is to map into this circle. And priority-based, you can choose if you want to prioritize on Q or P. Okay, this is a very popular approach. There's also anti-wind-up control loops for your PI control for voltage or current controllers. And there is a hysteresis loop. Virtual impedance is also another popular way to achieve current limiter and voltage limiters as shown here. For now, I want to just highlight that these various loops will introduce hybrid events, meaning instead of a smooth trajectory you would expect from a differential equation, now there could be saturation of your state. And if you think about the trajectory of the state, there will be a non-smooth change of your system behavior, right? And it can be reflected through this pseudocode of the logic. Say, for example, here it's describing the anti-wind-up for the PI controller. There's also current limiter, as we just explained. There's also limiter for the DC side signals, among others. Now, if you think about the paper you've read, I'm positive that you often see the model of power system using differential equation or differential algebraic equations, right? Is it possible to capture those hybrid dynamics we just described? It's possible if we extend it, because think about all these various events. There is a fault that could happen in the system where the transmission line trips, which can be thought as a triggering event. And say the voltage drops across the network, and your device, your IBR, respond. This could be thought as the consequent or responsive event. Okay, there's another inverter in the system that meets its current limits, and the system model or dynamics change because now it's driven by different physics. There is a circuit breaker that opens due to various faults in the main grid, and now your system topology changes. A generator could hit its reactive power limit because it has limited capability to supply reactive power. All these are events that classic differential algebraic model cannot capture. And accurate handling of this switching event is vital to have any possibility of recreating the complex power system behavior. Okay, so conceptually, we can think of them as a triggering event, the system response, and then after the system clears, we have this period post-event that's away from this event. So in these two papers, we propose a more general class of a system model that's called differential algebraic impulsive switch model, meaning you could have differential equations, you could have algebraic equations that switch before and after the event, where the event is described by a event triggering manifold. That's a function of your state. And your state could hypothetically also experience jump, for example, from this pre-event state to the post-event state. Okay, this is a much more richer class of system models. And here is abstraction or pictorial illustration of what happens before the event is met and after the event, your system follows follow a different vector field. There are more things going on here, which are describing how trajectory sensitivity changed, but let's not get into the details of that. Using this model class, you can capture, for example, here, when the reactive power of your generator meet its maximum amount. Now your system response also follows a different algebraic equation. So there's this non-smooth change happening over here. And from time scale, this is what you would see for the voltage magnitude signal. You can see this clear state jump and switch of the system behavior. Okay. Another thing that's important and sometimes omitted is the impact of transmission line dynamics. The conventional power system modeling ignores line dynamics, which is valid for slow synchronous machines, but not necessarily for fast-acting inverter-based resources that are operating on millisecond timescales. So there's this risk of ignoring the possibility of capturing instability when you don't model your system correctly. I'm not saying this is something you have to model. I'm saying that it is important to choose the right model for the system, for the problem you are interested in. And this is ongoing research development. So for example, here, the dynamic line model is capturing the electromagnetic transient during the differential transient period for the network current. Here I'm using a global reference, capital DQ frame across the power system. And here is the D and Q component of the current state flowing across the line. And this is a differential equation. There is a transient, there is a dynamics associated with this state. If you look at your current flowing through the line, you would see with time, this is a changing signal. At steady state, if you choose your global DQ frame to be the steady state frequency that your system eventually converges to, which is not necessarily 50 Hz or 60 Hz, you would recover a steady state value for these currents. And that's what you normally assume in conventional power system modeling. Okay, so now in this more general class of a model, your impedance could also be frequency dependent. Instead of in the conventional way, you directly assume this impedance value is mirrored with nominal frequency, 60 or 50 Hz. The difference may be very subtle, but this is something I want to point out when you decide what model you choose. Okay, so we've done a gazillion of numerical studies. Instead of showing you these curves, I just want to briefly summarize. This is a collaborative project with ISO New England in the United States. The official report is not published, so I ask you to, not maybe exercise caution when looking at these results. And if you want, you can cite the presentation because the report is not published. So we look at these different reforming control schemes for virtual synchronous machine-based GFM and Joule-based GFM. We consider different DC side modeling, including ideal DC side versus a DC link that potentially have limitations. For example, your renewables or your battery may have a limitation to their functionality, to their characteristic. Maybe the rate is limited or the energy is limited, things like that. So we modeled the anti-wind-up PI controller The AC side, the voltage controller with anti-wind up, we consider Q priority-based AC current reference saturation, and DC side, the current rate limiter, and the other saturation limiters for this instantaneous current. So we consider fault scenario of a three-phase grounded short circuit at the PCC point. And here are a range of important observations. I want to highlight that this is specific for the system we study, and please do not generalize at the moment. So we observe that the ideal and intermediate DC side modeling, they exhibit similar transient behavior without the consideration of DC limiter. Meaning if you assume your DC source is almighty or perfect, then the difference of the simulation study is small. However, when you consider this DC link behavior, they exhibit higher incursions and the slower recovery under the presence of DC limiters. And with the consideration of dynamic lines, you observe more oscillatory behavior compared to static ones. And furthermore, the Q priority limiter can ensure fault rest-through in almost all cases compared to P priority, and this is also industry practice. And this existence of anti-wind-up mechanism in voltage controller ensures a stabilizing effect. And in general, virtual synchronous machine is slightly lower than droop, but it exhibits a better damped response with reduced oscillations. So far, I explained the modeling considerations and some preliminary dynamic study focusing on these hybrid and discrete events that are important to inverter-based resources. Next, I want to spend the next, I think I have 40 minutes, on the fundamental stability concepts. So maybe you haven't taken a control theory or power system dynamics course, but let's focus on the fundamentals. Meaning we want to focus on the concepts and why and what does it mean to have a stable power systems and why it is difficult for power systems. Okay, so the classic stability framework for power systems focus on very detailed categorizations. So it focuses on the important electrical state, voltage, angle, frequency, because they are associated with important qualities we want to achieve. Although if you think about stability, it is a single concept. Later we will try to answer the question, why does power system study has to be so detailed, nuanced, and focus on these different concepts that are sometimes confusing, right? So in short, it is because power system is so complex that it is intractable to try to address all the questions in one shot. And we will materialize this comment later. So look at this voltage angle and the frequency quantities. They each correspond to important quality. For example, voltage is associated with power quality. If your voltage is varying, you may have flickers in your light. You may have this sudden dim of your light. And angle is associated with synchronization across the network. Frequency is something you can appreciate even more because it's associated with the balancing. The power generation and load has to be equal to each other at every instant. in your system. If they are not, you will have frequency excursions. And these states are controlled through various control schemes in conventional systems. For example, the automatic voltage regulator tries to control the terminal voltage to a certain set point. If there is a mismatch, you will change the exciter, the field voltage of your exciter on the synchronous machine to adjust this terminal voltage of your synchronous machine. However, if you want to achieve a very good performance, very fast voltage control, the high gain AVR may destabilize the angle dynamics. And some generators, they will add a so-called power system stabilizer to stabilize these dynamics. Okay, so frequency and the power balancing is achieved through governor, and then in the back end, the thermal process. You would adjust the power generation to achieve this balance in the network. Okay, and yet at the higher level, you have this economic dispatch or unit commitment to decide what is your objective, what is the best power profile you want to set for your network. So this is a very quick picture in one slide to brief you about the timescales and power system dynamics in conventional system. Okay, the timescales in conventional system are more or less decoupled because of this separation of timescale for voltage, frequency, and angle state. That's why for the classic power system stability, actually we published this classification as shown here, focused on the right. We now decouple the single stability problem for a power system into the study of this different dominated state, because we can afford this approximation of timescale separation in classic power systems. We have angle stability, voltage stability, frequency stability, and in different time scale, short-term, long-term, and different size of disturbance. I will also spend time later to discuss why the size of disturbance matters. Though in future power systems that are dominated by inverter-based resources, these are not something we can safely assume without getting into troubles. So the time scale, firstly, is no longer clearly decoupled for inverter-based power system because IBRs, they operate in faster time scales. The electromagnetic time scale of IBRs are of the similar time scale of your lines and filters. And now we are concerned about these instantaneous voltage and currents, which may be important in your dynamic study. There's this increased speed in frequency dynamics in the system. On one end, it's because of this reduced inertia of the grid. On the other hand, the increased speed of your IBRs. However, you may also often hear that reduced inertia is a problem in power system. Right? But now let's think about the physical example. Is reduced inertia always a bad thing? It means that your system can respond faster. The problem may come where you have disturbance in your system and you don't have the preparedness to respond. But this is a flexibility or design choice because your IBRs should have the capability. It's just like if you are clever enough to design the controller to achieve this goal. So technically speaking, you have more capability now. You just need to be careful and know what you should be looking for. Okay, so there's also indirect voltage control via injecting reactive power through your IBR to bump up or reduce the voltage at the point where this IBR is connected to. because reactive power's effect is more local. If you inject reactive power here in this bus, the effect is stronger at this bus and then decrease at other buses. And active power is more global, right? You achieve this frequency synchronization across a large power system network. And there's also this inner control loop that we discussed just now. So the timescale separation is not clear anymore. Now let's look at the stability concept. It is the most important property of a dynamical system. The most fundamental stability concept is internal stability, or Lyapunov stability. It tells you whether the system states can remain close and even better converge back to the equilibrium point after being subjected to a disturbance that perturbs your state away from an equilibrium point. Imagine a perfect world where there's no disturbance, and if you start from equilibrium point, you will just stay there forever. That's the ideal world, which is not true. So this concept of disturbance or change in your system is a critical consideration to understand the stability concept. I will go into details next slide. There's also other important stability concepts, such as BIBO stability, which only looks like the input and output portal. There's also structural instability. In the beginning of the lecture, we used one example to explain what is structural instability. Right? If you recall the green curve, that's fold back, and if you exceed beyond the bifurcation point, structural stability is lost. There's also solution space boundary singularity. If there's time, we can quickly get into that in the end of the second lecture as well. So why is power system stability analysis difficult? It is one of the most difficult problem because power system is large scale, it's complex, and it's most importantly nonlinear. Even more, there's could be hybrid dynamics, as we explained, right? So the difficulty associated with nonlinear system is bad construction, is by nature. So to analyze nonlinear system is difficult. You should expect the analysis of nonlinear system is challenging, as later we will see how complex the behavior could get. The analysis of linear system is much simpler because there are how many physical systems are linear. The age is linear, but your physical system like automatic car, power system, gas system, nothing is linear in this real world, right? So another challenge which can be appreciated through numerical versus analytical analysis. Let's say for numerical method where you numerically integrate differential equations. Okay, if you have a very high order system that's stiff, meaning the time scale scattered around vastly. You have very tiny time scale in the system and very slow time scale. Your integration step has to be smaller enough to capture the the slowest time scale for you to capture those dynamics. Okay, power system is a stiff system. So this is one challenge. Another challenge is to try to encapsulate or analyze the large set of scenarios. Say I have 20,000 nodes in my system. I have many transmission lines, many devices, and there are many scenario or operating conditions I want to study. But if I spend my computing resource in simulating these vast set of scenarios, I'm not going to be achieving that in the time scale I'm interested in. For online operations, it's not possible. Then let's look at this analytical method where you want to achieve systematic step-by-step understanding and hopefully also insight that can also generalize and apply to other systems. This is very challenging for nonlinear systems. and our hands are tight. I will use an example to explain this. So I mentioned that to understand the stability concept, we have to think about what change or disturbance that could happen in our system. Right? There are various disturbances of various natures. For example, the environment changes, the temperature change, your line parameters change. There could be equipment failure. There could be operators' intentional action to change the operating point of your system. There could be malicious actors' action that tries to target your power system. And then there could be longer type of disturbance or change to your system, like adjust the topology or system upgrade. You can think about these various disturbance across different time scales. In the fast time scale, microseconds, there is this operation of protection scheme. There's these various electromagnetic dynamics. And the millisecond scale, we have electromechanical dynamics. And then there are slower ramps of residual load. There's this energy supply change in the time scale of weeks or even longer. Okay, think about all this change that could happen to your system. Such disturbance can be categorized into small or large in nature, meaning how far the disturbance makes your system state's departure from your desired equilibrium point. But how small is small and how large is large? Is there a more clear understanding for a dynamical system? So let's think about linear system first. Let's consider x dot equals to fx, where f is a linear function of x, meaning f equals to a of x, where a is a constant matrix. In this case, in a nonlinear system setting, the size of disturbance is not important at all because the behavior of linear system is global. That means if the behavior is following certain pattern that's closer to your equilibrium point, it's also going to be behaving as this further away in the state space. Say here you have this flow vector field along this direction, but that's the same anywhere in the state space. Similarly here, you follow this trajectory, but that's global. And also for this system, everything is spiraling in. For this case, everything is parallel. All this situation is global. So the size doesn't really matter here. What matters is for our situation of nonlinear system. The state space of nonlinear system is separated by various structures. This is intuitive because if you think about one point in a state space, you've got to know where I can move, right? And if I have multiple equilibrium points in the state space, there's got to be a separates where I decide where do I go. So the state space for nonlinear system is separated by such structures. And more precisely, we can think about this important concept of region of attraction for nonlinear systems. I will show you an example momentarily. So for this nonlinear system, that's our class of model that we focus on, where f is a nonlinear function of x. Here, the size of the disturbance do matter because you may enter into a zone where you pass or exceed the region of attraction of your equilibrium point, and you will never be able to come back. So physically, that means your state will not recover to your desired state. Okay? And another important point is that for nonlinear system, we have to specify which equilibrium point we are talking about, precisely because of this reason. So for nonlinear system, for the post-disturbance states to converge back to an equilibrium point, it requires the following conditions. Firstly, there exists an equilibrium point. Again, think about the example I gave at the beginning of the lecture. If there's no solution, there's no equilibrium point, there's nothing for you to converge back to or even focus on, right? And this equilibrium point, post-event equilibrium point must be stable, meaning there is, in the sense of Lyapunov, meaning there is a non-empty region of attraction. And the post-disturbance point must lie within this region of attraction for you to be able to remain in the ROA. The formal definition of stability in the sense of Lyapunov is given here. Is a classic definition, is an important one. I probably won't spend time to explain it. I just want to mention this is the most important internal stability concept that we should base our understanding on. And if I want to describe it in one sentence, that is, if you are staying close, you remain close. That's an intuitive understanding of this stability in the sense of Lyapunov. So maybe you are familiar with this example, the single machine infinite bus system. And this is the characteristic curve. And this is the mechanical power input. And there are two intersections, means there are two equilibrium points. One is stable, one is unstable. The physics of this Smith system is similar to nonlinear inverted pendulum, meaning you have a pen, and the dynamics are similar to the rotation of this pendulum. So similarly, you have a stable equilibrium point and unstable one. And for it to be unstable means that if you put it away from it, you will diverge away from it. For it to be stable, if you move away, you slowly converge it back. Or if there's no friction, you continue to rotate. But that's also stable in the sense of Lyapunov. It's just not asymptotically stable. So this is the region of attraction when the damping is 0. You have a closed region of attraction. If you remain in the ROA, you stay within the ROA. So if your fold drives your state to evolve away from this equilibrium point, I want it to be cleared before I hit the boundary of ROA. That's called critical clearing time. If your fold sustains longer than that, then maybe I land at this point. I will follow the system dynamics and diverge to infinity, meaning I won't be able to remain close to equilibrium point. And this is a damped behavior where the D term is greater than 0 and the RA is open. But similarly, you have different type of behavior in the state space. This is different to linear system where everything is global, right? And that's why the size of the disturbance matters here. So in summary, the fault or disturbance on the system will force the states away from the stable equilibrium point. And the fault is sufficiently large, the disturbance will cause the trajectory to cross the boundary of ROA and stability will be lost. Here I'm using the term loosely. Basically, I mean convergence to your equilibrium point is lost. Okay. So here is application or analysis for a two inverter infinite bus system. Single inverter infrared system has been well studied for their transient stability. Here, I'm considering a system of this form where you could have two IBR connected via a certain line to this point, and you have a connection to your grid, which is represented as an infinite bus. And for any one of these IBR, I could choose from a mixture of heterogeneous IBR control, ranging from grid forming, grid following, or grid supporting, which is a mix of this characteristic for forming and following. And here is how complex it could get for this simple two-inverter infinite bus system. And again, think about your actual power system, which could easily have thousands of bus and transmission lines and various different components. So this is the region of attraction for this simple two-inverter infinite bus system, where this ROA is estimated using a manifold method. Briefly speaking, for your equilibrium point, you could consider the linearization at this point, and you would have a eigenvector structure at this point. And this eigenvector is an approximation of the stable and unstable manifold at this equilibrium point. The stable manifold for the unstable equilibrium point will give you a precise numerical estimation of this region of attraction, because the stable manifold of unstable equilibrium point is the set in the state space where moving forward in time, you would converge to this unstable equilibrium point. And think about the intuition I was trying to explain. In the state space of nonlinear system, your behavior is separated by certain structure, such that you can decide where you go, which equilibrium point you would be attracted to. So that's a maybe very high-level explanation of why this manifold method works. So this is considering the connection of two grid-following inverter connected at that bus. And these different curves shows different trajectories after subjected to faults with various system parameters. And that will affect the system's ROA shape and the critical clearing time, how far of the fault how far the fault can sustain such that it will stay within the ROA, which is the critical clearing time concept. So this is a method that can, in a sense, numerically estimate the ROA region. Although the concept is analytical, right? We are trying to get an insight or structure out of the system. The downside of this manifold method is that it doesn't scale for higher dimensional system, because this is basically a planar analysis such that you can visually look at it. In general, for high-dimensional nonlinear system, one of the most prominent method is Lyapunov function method, where you construct a Lyapunov function for your system such that certain conditions are met, meaning it's a positive energy-like function, and the energy along your trajectory is decreasing, roughly speaking. So you can use this energy function to estimate. You can use the sublevel sets as an approximation for the actual ROA of your system. For example, look at here. This is a so-called controlling UEP. Meaning if you evaluate the sublevel set of your energy function at this, using the energy at this point, that is a conservative estimation of the true region of attraction. more details can be found in the literature. Okay, so are we done with this task? That's not reasonable to expect because if your system is difficult to analyze, it's going to be difficult. It's just that you may be able to shift away this difficulty to some other part. And in this method, the difficulty is being shifted to finding a Lyapunov function. After you find a Lyapunov function, the task is easy. You can get a conservative estimation, meaning that you have confidence. If this is certified, the actual system will be stable. And you can get very fast online estimation because now your task is purely algebraic numerical evaluation of your energy function instead of time-consuming numerical integrations. Okay, so maybe I want to add some comments here. The study of GFM, grid forming inverter, using this energy function-based method is relatively easy because you can leverage the existing tools developed for conventional synchronous machine-based system. If you map or link your dynamics of grid forming properly to the synchronous machine's dynamics, especially for virtual synchronous machine. To try to use this method for grid following has a inherent difficulty in the sense that the PLL introduce a sinusoidal term that is similar to the role of transfer conductance in power system, which eliminate the possibility of finding a global energy function, and which is the most advantageous application. So there's this inherent difficulty there. Okay, although we can still do some numerical approach, we can perhaps find an approximation and numerically construct energy-like functions. Another challenge in practice is that this method, the conventional method of energy function, assumes detailed timescale model. So again, as we mentioned before, to get a detailed model of IBRs is challenging because they are proprietary, right? And also you want to make sure your parameters are right. You're working with a model that's good enough. All models are rubbish, some are useful. So this is another important consideration. Okay, so the last point I want to highlight is in practice and in your analysis, you oftentimes use linearization of nonlinear system. How can linearization be justified? It's not arbitrary, right? We use it because there is some confidence we can get out of linearization approach. Other than accuracy, if you remain close to your approximation domain, you get an accurate approximation. There is also an important theoretical bridge of the stability of your linearized system and the stability of your nonlinear system. That's what justifies using the stability analysis of linearized system for your original nonlinear system. And the theorem is presented here. We consider an equilibrium point of nonlinear system because, again, for the stability analysis of nonlinear system, we're not talking about the stability of the entire system. We're focusing on which equilibrium point we are analyzing because of that structure I explained. So consider this nonlinear system x dot equals to fx, where f is a continuously differentiable function near the origin. Let A be the Jacobian matrix evaluated at this equilibrium point. Then the origin of your system is asymptotically stable if all the eigenvalue of A have a strict negative real part. The origin is unstable if there is at least one eigenvalue of A that has positive real part. We don't know anything based on this theorem if the linearized system has eigenvalue on the imaginary axis. Okay, this is a theoretical bridge that justifies the linearization. So I started when? How long do I have? Yeah. Oh. Okay, so I have something prepared for structural instability. But according to my timer here, I already talked about the 70 minutes. So probably I should stop here and take some questions if there's any. Yes. You mean the convexity of the energy function? Not necessarily. The conditions for energy function or the atom function is just that this function is positive definite away from the equilibrium point and only is zero at the equilibrium point. And another condition is that the Lyapunov function is decreasing along the system trajectory. So there's nothing of convexity of the structure of the definition. However, if you like, you could restrict additional constraints for the Lyapunov function, which may cause you some conservativeness in using this Lyapunov function to estimate the region of projection, but which may bring you extra benefit if you need convexity. Yeah. Okay. Any other questions? Yes. Yeah, in short, no. It's very difficult. As I mentioned, the difficulty now is shifted to finding the Lyapunov function. For conventional power system, there has been, many years of history where people try to find a meaningful Lyapunov function, specifically for a synchronous machine-based power system that assume uniform swing dynamics for synchronous machine at a certain node of your system and certain model for the load. For this, people have found a very ingenious structure-preserving energy function, and that was, I believe, developed independently by two groups back in the days. I think one of the group was the academic grandfather of mine, but this is something that you shouldn't assume you can achieve. But there's always hacks that we can use to get away with it. For example, in one of my earlier work, I used numerical construction to progressively expand my numerically built Lyapunov function and use this to progressively enlarge my estimation of the region of attraction. So these things exist. Back in the days, computation was a challenge because I was using sum of square, and I was applying to a system of 12 state, and the solver need to spend some time to construct this Lyapunov function. By the way, in the second talk, I will also talk about control barrier function, which is a similar concept, but it's used to certify safety. So in short, this is a difficult approach. We are making some efforts in using this method to analyze inverter-based power system. The plot I showed is a manifold method using geometric approach. We're also thinking about having firstly a simplification or abstraction of your system to simplify this step such that the follow-up construction of energy function could be easier. So this is ongoing research efforts. Okay, yeah. Other questions? All good. Okay, if that's the case, we can have a break and let's be back whenever Lucia told us to. Thanks. Thanks. Okay, so welcome back. We are already a little bit behind on schedule. So let's catch up, and I don't want to stand in between you and lunch. So here is the second lecture, and the focus will be on advanced topics. In the first lecture, we covered the fundamental concepts of stability, the modeling, the dynamic understandings of future inverter-dominated power systems. In this lecture, I will cover a few recent research projects in my group, and to basically demonstrate the open questions in the field, and also hopefully to inspire you for potential future research topics. So here's the outline. I will begin by introducing a project on scale-free decentralized stability and its role in stability-constrained operation. And then the second research topic is safety critical grid forming control with assignable voltage behavior and strict current limiting. If time permits, I will talk about a interesting project using differential geometry to study the singular solution space boundary using geodesic curves. Okay, the first one, scale-free decentralized stability. Traditional approaches for analyzing small signal stability in power systems includes eigenvalue computation or frequency domain approach using Nyquist-based analysis or among others. They require entire system models, no matter it's a state space or frequency domain, which could be high dimensional and nonlinear, especially for future large-scale multi-converter systems. And they also depend on your operating points and network condition. With the increasing shares of heterogeneous power electronics devices, the global analysis will be challenging for future systems. Specifically, why could centralized analysis fail to scale? Firstly, as I mentioned in the first lecture, your analysis is for a set of conditions. With the future system that sees high shares of renewables and flexible loads, you are expected to see variability of a higher scale and faster time scale and larger in size. So it is challenging for our analysis because now your analysis need to be robust to a larger range of operating point variation. And secondly, with the higher number of smaller scale inverter-based resources, for example, in the past, you may have 10 large-scale synchronous machines with a limited number of states. Now, suddenly, you have a higher number of dynamic states for your system, which is what I would refer to as increased system dimension. So the complexity also increased. Our method should be scalable to the detailed modeling of numerous IBRs in this situation. And thirdly, consider the quickly piling up integration queue for AI data centers and other EV charging stations, and in general, the increase of load. If you have a new device to your system, that means your system model changes. the analysis you did before for the entire system may need to be redone for this case. So ideally, we want a method that is adaptive to plug and play of the devices in the system. And last but not least, as I mentioned, there is this issue of lack of transparency in control implementations that's specific for inverter-based resources. The decentralized approach, though, ideally could only rely on local information that does not require the sharing of this information between devices. And I sort of separated the task of system operator and individual device. As a system operator, I ensure my system topology and the parameter and structure follow certain expectation. As the local device, I only need to ensure that I satisfy the criteria that's given to me from the system operator. And my goal is to certify system-level stability using limited local information and can be checked by individual devices. So looking at this figure, this is an abstraction of my system where the feed-forward path collects the models of my individual device on the diagonal blocks. So each of these blocks is a transfer function for my individual inverter-based resources. And they are collected in this fashion. Because they are block diagonal, there is a certain level of decoupling between each other naturally. And the coupling are achieved through the feedback loop of your network. So in this case, your network could be modeled by Kirchhoff's current law. And this function L would be the Laplacian matrix of your impedance. And the 1 over S comes from the fact that we are considering angle and the voltage dot, the derivatives of voltage magnitude that I will explain in the next slide. So the system equations are abstracted into this form. And a standard approach to achieve decentralized stability is through passivity. It says that if your device G, which is a dynamic device sitting in one of the blocks, if each of the device is strictly passive, then their interconnection is stable if the network model L satisfies this condition. It could be anything as long as it's within this set. Though a common issue with passivity-based approach is that it could be conservative. And another common issue is that a lot of devices are not passive. So passive is a strong requirement for devices with source. For example, battery, those devices with a input. And many physical systems have a delay. System with delay, they are not passive. So in this work, we based upon a extended passive condition. And in this paper by a collaborator, it's also shown that this is, in a sense, the best, the most least conservative decentralized criteria if you truly are not wanting a information sharing. So what's it explained can be seen from this figure. So conventional passivity requires the Nyquist plot lies strictly on the right of this imaginary axis. This result shows that if I can find a multiplier H that is positive real, then I can relax or extend this condition to a situation where your Nyquist plot can be slide anywhere downward this hyperplane. So this is a much relaxed region compared to the half plane on the right of imaginary axis. That's where the extension or improvement come from. So if I can find or construct this multiplier, then the condition I would need to enforce on my individual devices is that these local inverter-based resources are stable. This is the theorem. The test you need to perform is essentially that I want to find a H such that this expression belongs to extended strictly positive real, which is a technical term. We don't need to worry too much about it. And the entire system is stable as long as your network condition lives within this set. So zooming into more details, the network model is described by this matrix L, where it is a decoupled linearized power flow, decoupled in the sense that I'm assuming the off-diagonal term of this subblock that couples between this variable of P and V, the magnitude, and the coupling between the reactive power and angle are 0. This is motivated by the physics of high voltage transmission system, where the transmission lines can be assumed to be lossless. This is not something you can assume for low voltage distribution systems where loss is not negligible. And furthermore, a typical assumption is that at equilibrium point, the angle difference across each transmission line is small. Small here is in the sense of between 0 and pi over 2. So it's not a very restrictive assumption because this is assumed for equilibrium point. This is a classic assumption. And I assume my transient voltage magnitude lies within this bound of minimum voltage, Vmin and Vmax. So the expression of this term, the partial derivative of active power with respect to angle is given here. And similarly, of this expression Q sub V is given here. One of the main contribution of this work is that we extend the network model to consider also this QV coupling. The conventional work, the previous work, only considered the coupling between active power and the angle, which essentially ignored the reactive power and the voltage magnitude loop. So this is our system structure, which is a realization or instance of the previous abstract system I showed in the previous slide. Here in this system, the input is the delta of active and reactive power, which means the displacement of your active and reactive power away from your equilibrium point. Again, linearization around this equilibrium point. And here is the bus dynamics. The diagonal transfer function block that you saw in the previous slide. The output is angle dot and voltage dot, which are then fed through this network model to give you this relationship of P and Q. This is the interconnection to represent your power system model. Any questions? Okay. And the dynamics of these inverter-based resources are in this work specifically for droop-based grid-forming inverters. So looking at these models, these describe the droop-based, meaning you have a droop relationship between your active power and the frequency. Here, F FP and FQ are the filter used for filtering your active and reactive power measurement. Okay, and the omega I0 and Vi0 are the set point for your frequency and voltage magnitude. So those set points could be decided by a higher level problem. For example, you could solve an OPF to decide the optimal profile for active and reactive power and voltage for your network. And for this stability project, we are taking that as a constant set point, and we study this linearized model. We study its stability. So the resulting criteria is given in this theorem. I want to draw your attention to this condition to firstly notice that this is decentralized in a sense. Your variables are either your local variable with the index I or its immediate neighbor with the index j within this set calligraph n, that's the neighboring set of your local node. So the left-hand side is the voltage difference between this node and your neighbors. And this is a control parameter. Beta is your filter gain. And the droop is for the reactive power loop. So let's focus on this term. And on the right is your network BI term, which is a summation of all Bij connecting to your node. So this is a nice structure in the sense that it links your operating point with your control parameter and with your system parameter. So let's think about the physical meaning of this BI term. In a strong grid, I'm using this term loosely, we consider a small BI term, right, which gives you a larger right-hand side. Okay, so now your range for the droop parameter is a larger set. Okay, now we think about a droop relationship between Q and V. With the same amount of Q, if you have a larger M, you would have a larger voltage variation. Conversely, if you have the same amount of Q variation and a small droop parameter MQ, your voltage variation would be smaller. That means you have a stronger voltage control for your inverter-based resources. Right? So this is the interpretation of this constraint, this criteria, back to your physics of your IBR. Your devices may have various levels of capability for voltage control. It may be able to achieve a stronger voltage control, meaning voltage displacement is smaller. Maybe it has less capability of voltage control, so this is more variable. So this basically gives you an interpretation using these decentralized stability criteria of the requirement for the voltage formality of your droop-based grid-forming inverter. So we think that this BI term can also be interpreted in a sense as denoting the strength of the grid, but I want to highlight that this is not precise, this is just an understanding. Okay, the next step after we develop that decentralized stability criteria is to understand how good is the quality of these criteria compared to the true eigenvalue-based criteria. So look at this two best example. We also have the results for larger system, but this is easier for illustration. These different figures shows the result with different parameter for the transmission line for the B term. And each point on this plot represent a ratio on the blue curve, represent a ratio of how many points at this of a grid around your operating point satisfy the decentralized criteria. Satisfy the true small signal criteria, but does not satisfy your decentralized stability criteria. And recall that the decentralized stability one is supposed to be a sufficient condition. So I'm only focusing on here the gap, the conservativeness of this stability criteria. So ideally, I want this gap to be small, but not too small, because there may be parameter mismatch. There may be other considerations. So I also want some room of conservativeness here to enhance my confidence of using these criteria. So the orange curve is showing the worst eigenvalue in the system for this grid of operating point that I'm studying. So as soon as it crosses this 0, that means it's crossing the imaginary axis. I do not care about it onward because the actual system has the point that's unstable. I also want to, I only want to understand this part where the droop parameter is reasonable per the engineering rule of thumb. Okay, so it shouldn't be too large. This MQ, the droop parameter between reactive power and the voltage. So you can see that it's a somewhat conservative and perhaps comfortable zone of 40 or 30% at this far end, and maybe less than 30 when MQ is small. So this is a step after you perform certain analysis to verify the quality of it against a benchmark. Next, the next structure of this decentralized stability criteria motivates us to use it in the operational problem, because again, the variables that appears in this criteria are for this operating point that is determined by your operational problem. The classic OPF or operational model typically only consider power flow equations and some operational constraints, including thermal limit, line flow, operational limit of your device, such as voltage, upper and lower bound, ramp-up limits, among others. However, stability is not conventionally incorporated in the operational problem. The classic operational scheme assumes this hierarchical operation where the higher level operation problem take care of the decision for finding an optimal profile for the operation of the system for the next 15 minutes or hour in the inter-day economic dispatch. These variables in your OPF problem is the subspace of the full state space in a dynamical system. You consider active reactive power, voltage, angle, right? In the dynamical model we discussed in the first lecture, we also have various states that are inherent to your inverter, that are associated with your control, right? All these are not considered in the classic OPF problem. Then why does it work? The classic operation uses this higher level operational problem to determine the operating point and assume that whatever problem that's left can be taken care of in the through the lower level dynamics and control. This would work if you are far away from the stability margin, if you have a lot of room to wiggle in that operational timescale. However, if you are close to the stability boundary for various reasons, maybe fault or event, or this increase of the load, which push you towards the stability boundary closer and closer, this is something we should reevaluate. And furthermore, with the loss of timescale separation, can we still assume a operational scheme of 15 minutes, or even push down to the 5 minutes? Is this appropriate for analyzing the variability in your system? So that's what motivated us to leverage the nice structure in the decentralized stability criteria in the operational problem. The existing approach to study stability constraint OPF oftentimes assumes an abstraction of dynamic understanding. For example, through various metrics such as Rokoff, nadir, and other abstracted metrics such as short circuit ratio. They are a approach to get away of handling the detailed dynamic in the operation problem, because that's not tractable in optimization. However, that's also not the precise characterization of stability. So other approach of characterizing the actual stability, say using eigenvalues, they face computational challenge because computing eigenvalue is not an easy task, especially for large systems in optimization. And furthermore, they also assume global model, and there's no analytical expression with system higher order than a digit number. So in practice, how system operators deal with this philosophically is decouple these two problems. I solve my operational problem, and then there is a hierarchical layer that's offline, where I evaluate the scenarios to cover a range of important situations that's relevant to my specific system. Because they've been dealing with their system for such a long time, they have a good understanding, which helps them to screen the important situations, say which generator moves up and down. But there could also be loopholes, right, as we face more and more complexities. This process is also time-consuming. So various challenges in the existing approach, including approximated stability characterization, numerical complexity. And the last point is an interesting one, because that's what I want to get into. A lack of interpretation of the economic value of stability service for individual devices. If you capture the stability using eigenvalue or various other metrics, there's no direct linkage between the contribution of individual devices to this stability certification. And that's an interesting point that I want to explain more later. Okay, so our key idea is to use this decentralized stability criteria as a efficient characterization of the stability contribution of individual IBR in OPF problems. So we incorporate this additional stability constraint in conventional OPF problem. This is a simple example. There is more general formulation. The advantages are immediate. Firstly, these stability conditions are sufficient conditions, meaning if these stability constraints are satisfied, the true system should be stable. Recall that quality check I presented. And secondly, because these stability constraints are decentralized, meaning it is linking your local system state with your neighbors. Everything is decoupled, meaning in your OPF, you have decoupled constraint, decoupled algebraic constraint in your OPF problem. That provides a very direct interpretation for the economic value through the shadow price. So we defined a nodal stability shadow price as here, which is the summation of the shadow price of the dual variable of all the constraints associated with your node. So your node may be connected to multiple different neighbors, and each of that will lead to a constraint here, and that would give you a dual variable. We proved that you can use this summation as an interpretation of the essentially the maximum over voltage constraint. So the details can be found in this preprint. So we ask a few key theoretical questions. Firstly, does decentralized stability constraint affect OPF decision, or is this a non-problem, something we imagined just because we noticed some nice structure from our stability constraint? And secondly, when does it introduce a trade-off, if it does? The third one is, what is the economic value of stability service? Is stability provision costly or not? So the first theoretical result is that stability can be free, but hear me out. This is under the specific settings we considered. So firstly, we assume a lossless network as the assumption we used in deriving this decentralized stability criteria. It's important to remember where you came from and keep track of all these important assumptions you made along the way. So we assumed the lossless network. And in this case, we are only considering the cost for active power. So this is a P-only objective, which is also somewhat typical in classic OPF literatures. But later, I will discuss what is the loophole. So we consider this class of voltage-dependent, voltage difference stability criteria as what we developed. So here, the expression is slightly more general than the precise form I presented. So this first theorem shows that the stability constraints may be active, but it will have zero shadow price. So can you think about what does that mean? When I add this constraint to my problem, it may be binding, but there's no shadow price associated with this constraint. So basically, this doesn't trade off with my objective function. And in a sense, this is free stability achievement. But I don't want to be misleading here because firstly, there are assumptions in the setting. And secondly, I didn't consider a very important factor that your IBR has dynamic operational characteristics. And the provision of reactive power is, in a sense, an opportunity cost because your device have limited capacity. And if I use reactive power, I'm reducing theoretically my capability to produce active power, which a lot of practice are putting a price for. So here, there's no cost designed for reactive power. And then we have this result, which is somewhat counterintuitive. And the second, here's the proof, I will skip. and you can find it in the paper, in the preprint. The second result is what I really want to spend some time to discuss, because in this situation, we do associate a cost for the reactive power generation from the inverter-based resources. And in this case, the stability does become economically relevant because it now conflicts with your optimal dispatch direction. So this is a situation where you take into consideration of the dynamic characteristic of your device, and that gives you a more reasonable interpretation of your system. So the previous result is nice. We can say stability is free, but I would argue that this is misleading because you didn't consider important dynamics and characteristics in your devices. So this is the result where I want to highlight to consider the opportunity cost of reactive power in inverter-based resources. So the third theoretical result, we just basically construct the condition for when stability will introduce this trade-off. So mathematically speaking, that's also simple. It's basically just finding a direction where it interfere with the gradient direction of your objective function. If you only have active power, there's no trade-off. We introduce this reactive power, and this is a specific example where there is conflict of this direction. There could be many other cases where this conflict could happen. So here's a numerical example, again using this two inverter for illustration. Lossless AC OPF. Objective function includes both P and Q terms, and in addition, this voltage difference stability criteria that is dependent on voltage difference. This gamma is this term in our decentralized stability that's dependent on your control parameter and system parameter, right? And the base case is a binding case where this stability criteria is active, and it has this associated objective optimal value. When you relax this constraint, I'm also giving you a binding case, but with reduced objective function. And when I remove this additional stability constraint, of course, the optimal value also decrease. This is where adding a stability constraint does affect the optimization decision in your system. So in this project, we firstly construct a decentralized small signal stability criteria, and we notice this structure, and it motivates us to investigate this problem of when or whether stability is a relevant problem for operation. And we also show that it's not always costly, but this more reflects a formulation limitation rather than a true property of your system. When this stability does affect your OPF decision, we can quantify it using the nice structure and associated dual variable of your constraint. And lastly, I want to highlight this physical importance of your device, the opportunity cost of your IBR's reactive power. Okay, so I have time to discuss about the second project that's on safety critical grid forming control. This is a control theory focused project where we focus on important control problems that are relevant to your device and to future inverter-based power systems. The first one is a voltage source behavior that should be enforced by grid-forming inverters. We want to achieve through control design a nice voltage source behavior from your GFM inverters, and possibly under uncertain grid conditions and unknown line parameters for your system. Anything beyond the PCC is not something you should assume you have perfect knowledge for. The other important question is current limits. As I mentioned, it's important to ensure your actual current flowing out of the VSC, the voltage source converter, is within the maximum current limitation. And as I mentioned, the typical engineering approach, they are not able to ensure that. So looking at this structure, we want to ensure the current at this point, because this is the current that's flowing out of your power electronics, to be bounded by the safe limit. And typically 1.2 is a good estimate. This is any controller that you're interested in or you want to design. So basically, later I will show that we will have a modified safety filter attached on top of this channel, such that I can ensure strictly this current state is within the safe limit. The classic approach where you map this reference to be within either the rectangular box or the circular box, they are not able to achieve that. So the state of interest are these list of electrical state collecting your current and voltage at in your system. Okay, you can try to match this IT at this point. Okay, VC at the PCC point, and the grid current. The control input for this control design problem is to form this internal VT variable in the DQ, in the local DQ frame. And the outputs to be regulated, as I mentioned, we care about this voltage formation at the PCC point. That's also the stipulation that's being enforced in various grid code I was trying to show briefly earlier. And disturbance in this system that we want to be robust against are this bounded but arbitrary grid signal and these system parameters. And furthermore, we want to achieve this safety constraint for the current at this point. That's the control setup. Here is a more detailed illustration of the droop control loss, which take place of these grid interacting functions in the generic scheme I showed earlier. And that's the classic droop relationship between active power and frequency, and the droop between reactive power and voltage magnitude. We designed this nominal, I will explain why we call it nominal, voltage controller and current controller based on a nonlinear control design approach. That's a backstepping, which is classical, and DADS, which is a more advanced control techniques. In short, the DADS design is a dead zone adapted disturbance suppression scheme, where I adaptively adjust this control input signal such that this control action only takes place when I'm a certain amount away from my nominal value. This is a critical step to get away with a common problem of adaptive control. So let's focus on, in the end, what can we get, which is a assignable performance specification. This epsilon is something you can choose, such that my VCC voltage can be converged into my desired value into this epsilon bound. This is what assignable mean in the title of this subsection. So what about safety of currents? As I hinted before, this is basically a safety filter approach, where after I compute this reference point from my nominal controller, I will furthermore adjust it or modify it such that safety is respected. And specifically, this is using control barrier function, which is a function that shares certain similarity with the construction of Lyapunov, but with a totally different objective. Barrier function is trying to forbid you to enter unsafe region. Say, consider I have a set that's dangerous, that I don't want my state to enter. What I can do is basically to create a barrier, a very steep barrier, such that if you try to exceed this boundary, there will be a very high penalty for you. And mathematically speaking, let's look at this barrier function construction Hx, which is Imax minus your state it. Meaning within the safe set where your it is smaller than Imax, your H function is positive, right? So I define this safe set as where Hx is non-negative. So basically, the next condition I need to enforce is that whenever I'm in the set, meaning I want to start from the safe point, right? If I'm in the safe set, I want to remain in the safe set. So that's why I have this CBF condition, which is similar to this decreasing energy in the Lyapunov function setting, right? But in this case, I want my H dot to be greater or equal than some value, which is a little bit subtle here. But for simplicity, let's consider H dot to be greater or equal than 0. My energy is only increasing. So if I'm in the safe set, my energy is always higher than 0. But this is also important technical detail. So this problem can be formulated into a QP, quadratic programming, and there is a closed form solution which is written here. So closed form expression is always better because you don't really want to solve this optimization in real time. You want a direct execution or evaluation of algebraic equations, which only cost some negligible computation resource rather than solving OPF, solving optimization problems. So what we get is for any locally Lipschitz nominal control, and the earlier backstepping DAS control is one particular example of the nominal control. Then any remaining states in my system and other electrical states are bounded and the safety are respected. So by construction, my currents are within this Mx. And here are some numerical examples to show that when there is a fault happen in my system where the grid voltage is forced to 0, meaning there's a short circuit fault during a certain period of time, you can look at these different curves for your electrical state of VC. they eventually converge to this epsilon bond. And this epsilon bond is something you can assign. Okay, on the right is the current. Without the safety filter, your current could exceed this safety limit. And when safety filter is added, for both a classic PI controller and our designed nonlinear controller, the current safety are respected. However, something to note is you want this current saturation period to be as short as possible. And in this case, the DAS-BS controller is able to recover from this current saturation faster than the classic PI controller. Okay, so that's the second research project centered around this important problem of current saturation. I think I'm on time for the schedule, but we also started late. So maybe I quickly talk about these research projects where I'm particularly interested in, and I think it could be interesting for you as well, which is on understanding the singular solution space boundary in power systems. And we're using geodesic curves. And the most recent work used limited data around a single operating point to achieve estimation of the singular solutions space boundary. So the memory should be fresh. This Iberian blackout in 2025, which turns out to be, after this analysis by the committee, a voltage instability problem, unlike what people assume or suspected to be a renewable-related low inertia event. So what happened was, in fact, a overvoltage problem with a multifactorial origin. The system had insufficient voltage control capability, and oscillation occurred in their system that affected the operation of the system, and several generators were disconnected, in some cases improperly. There are suggestions in the report to allow asynchronous installations to apply power electronics solutions to manage voltage fluctuations. The point I want to make using this example is, when would power system collapse? I mean, there are complex dynamics, evolution when certain events or fault happens, but eventually the power grid collapses because it meets a point where it cannot sustain any longer. So a mathematical interpretation, although a lot of simplifications are applied here. But the understanding is that you enter to the point where slightly beyond, by adjusting certain parameter, your system does not have solution, and your system cannot sustain longer. So let's look at this interesting figure, which gives the power flow solution boundary for a simple 3-bus system. If you have the same number of equation and unknown, you should have a unique solution for a system without considering the degeneracy. If you relax one variable, so you have more variable than your equation, then you increase a dimension of the possible solution manifold for a system, right? So for this 3-bus system, I'm plotting a solution boundary where I relaxed on this axis the reactive power set point of generator 2, and on this dimension the active power of generator 1, and this is active power of generator 2. So any point on this surface should be a solution for my system. So the power flow equation are in this standard form is given here. The power system in the physical world, they have finite capability to transfer power across network to supply loads. This is known as maximum loadability. And the voltage collapse will occur when the load and dynamics, again, there is more intricate dynamic process associated, attached to this voltage collapse. But eventually, if this load and dynamics attempts to restore power consumption beyond this capability of the system, your system would collapse. So our aim is to find this solution space boundary, which implies, in this sense, the stability margin of your operating point. Traditional method includes continuation power flow, which progressively trace along this surface or this manifold until you find this node point. There's also numerical optimization, where I directly look for this closest distance, but it could not give you the entire understanding of the shape of the of the power flow manifold. So both have their limitations. The continuation power flow is a computationally expensive method, although it can give you the entire shape of the power flow manifold. So the idea in this work is to use geodesic as a unique parameterization of the power flow manifold. When you consider a coordinate definition, you need to make sure that you have a unique coordinate matching. So geodesic is one of that object. So basically, geodesic is the shortest distance connecting two points on the manifold. It's not the Euclidean distance, which is the shortest distance. This is the distance on the manifold. And here is the description. So without going into too much details, we were using this geodesic as the coordinate, and by leveraging its description from the differential geometry, we construct an efficient approximation of the curves on the manifold, which is given here. And this is second order because of the geodesic equation here. And for quadratic function, we have an easy way to compute its extreme point. And that's what we used to estimate that fold point. And it turns out to give us a very accurate capture of the uniform shape of this stability boundary, although there is gap. However, I think for this you can address using heuristics. For example, if you use expensive CPF to construct the ratio of a particular point, and you can use this ratio to address that conservativeness across this all possible parameter combination. So essentially, this method is trying to speed up, because this is all possible parameter variation, for example, associated with any direction of your load change in your system. And the speed up is given here, comparing this different size of the system with different approaches. So compared to, let's say, classic continuation power flow, the speed up can be about 1,000. So our current work extending these results I showed here is that we are using limited number of data points around your single operating condition to numerically construct those differential geometry quantities. And in the latest preprint, which you can find online, we show that surprisingly you can use this limited number of data to construct the global information of this fault point. Although I think the most challenging and interesting problem here is to consider this limit-induced behavior. Everything here is smooth because we are using tools from different geometry. So I believe it might be challenging to try to address those important limitations and hybrid events, like I mentioned in the previous lecture. I do need to stop now. Thank you so much for your attention. And I want to conclude by saying, I hope you think and you agree with me, this is a very interesting and important area. It's a very diverse area as well because the industry is evolving. And we have many opportunities to apply our tools, and the system operators are finally interested in listening to what tools we can develop. Also, you can see that there are a lot of open questions and the theoretical insight we can try to develop. So with that, I conclude my talk and welcome any questions you may have. Any questions? Yes? The terms on the left? Sure. Okay. You mean the left-hand side of the stability criteria. And your question is? Okay. So the immediate neighbor. So your local bus and your immediate neighbor, but in the Crown-reduced network. So it doesn't mean these bus are close to you in the real physical system. Yeah. Other questions? Yes? I see, I see. So there are two questions, right? The first one is the time scale of how often we solve that OPF. I'd say the original time scale you would solve for your OPF and how often you can handle for your system. This should be something in addition, but not huge. Because of this constraint, the structure of the constraint we incorporate, we're not incorporating a difficult eigenvalue calculation problem. This is just and also linear constraint in your decision variable, the voltage. So in this current problem, the right-hand side is constant, is a parameter of your control of your system. Those are not yet the decision, but they could. But this is the addition of the computation compared to your original OPF. So that's actually one of the motivation why we think this is valuable because of how good this stability criteria fit with your optimization structure. Yeah, yeah. And there's another question. I forgot. Can you repeat, please, briefly? Oh, can you wait slightly? Let me finish this question very quickly. Yeah. Oh, sure. Yes. So the question we need to think first is what is relevant and what is important to the system. So the first reasoning we did for incorporating stability in the operation is because we think it might get relevant with this variation of your operating point, with this different change in your system. As for planning, it's for multi years. I do think you need to incorporate certain consideration from the dynamic. And I think the best scenario is you should incorporate whatever you can, as long as your computation is manageable. But long-term planning problem is already challenging. We consider scenarios up to 10 years. And I'd say you need to exercise more decision whether it's worth it and whether it's relevant. Yeah. So this I'm not sure there's a clear answer just yet. Yeah. Sorry for the interruption. Continue. Your question is, can coordination of IBR achieve that? Um, I think it's not a fundamental challenge from the dynamic and the technical side. So theoretically, I think it's doable. I think the challenge may comes from more practical considerations, how you um, how you enable the coordination across a different owner. And after you achieve certain service, how do you compensate the people for providing that service? And can you do it in a fair and reasonable way? So I do think maybe it's a more of a challenge on that level. Yeah. Thanks for the question. Any other questions? Okay, so thank you so much for your attention, and feel free to reach out later through email or during this week. Thanks.